All right, so today we'll finish up section 4.5. Some of the things in the section I'm going to give you the answer to, especially if it involves the calculator, because I don't want to spend too much time on that since we kind of did that last time. So remember, when we're using a graphing calculator, we can calculate a line of best fit. What are the two things that you need to find a line? To determine a line. You need to know the slope and y-intercept. Okay, and the calculator, I might still have it saved. I don't know if I do. Nope, I don't. But those might be different numbers. Those aren't the ones we had. But the idea is you type the numbers into this list, and then it can automatically calculate for you. LIN stands for line. And it can find a line that goes right through those points. When you do that, what does the A represent? Yeah, we usually call it M, but the A is the slope, and the B, that's your y-intercept. All right, so this first problem says the table below, and I'm just going to give you the answer because we need it to do another example later on. But it says the table below shows the number of teachers and the number of students at a school. So you kind of notice a pattern. The more students in the school, the more what? Yeah, they have more teachers. Okay, higher number of students, higher teachers. And if you typed all these numbers in and all these numbers in on the calculator right here, and then did what I just did, it would give you an answer of y equals 21x plus 42. So you guys have a blank line right next to the table that says y equals. Okay, write in 21x plus 42. Okay, that's the answer that you would get if we did it on the graphing calculator. I need one. What's that? A book? Because we give you homework worksheets instead of problems from the book. All right, so what does X represent here in this problem? Teachers. So X is teachers. And what is Y? Students. So what we could do is we could use this equation to make predictions. You could say to me, let's say I have a school with 320 students. What letter would I plug that in for? 320 students. Jordan?
Look at the titles of the chart.
Students. Why? If I plugged in 320 students for Y, I'd be solving for which letter? Antonio?
X.
And what would X tell me?
Number of teachers.
The number of teachers. So what you can do is use this equation to make a prediction. Okay? Because we don't have any data for 320 students. But you could plug it into this formula and say, well, if the school had 320 students, based on the data that I do have, I can make a prediction how many teachers would be in that school. Right? Now, what if I said to you, a school has 25 teachers? Where could you plug in 25 for what letter? Shannon? X. And if you plug in 25 for X, that would give you a prediction of what in the school? Yeah. How many students? So we can use this formula to predict how many students we would have or how many teachers we would have. Okay? It's not exact, but it's based on the data we do have. So, using, and you guys have a spot for this on your notes. Okay, it says using a graph or its equation 2. You guys have to write in this part. Okay, using a graph or its equation to approximate a value between two known values is called interpolation. So interpolation is making a prediction
Interpolation.
between two known values. All right, so if I look at this table of teachers and students, can somebody give me a number of teachers that's not in this table, but it's somewhere between 10 and 18? Give me an amount of teachers somewhere between these known values, but it can't be one that's in that table. Yep, 11. So if I plugged 11 into this formula for x, okay, what I could do is this. I could say 21 times 11 plus 42. I would predict that if there are 11 teachers in the school, there should be about 273 students. Okay? That's based on my prediction. Now, it might be off a little bit. It's not always going to be perfect. But based on my formula,
Just an estimate.
it's an estimate. So what I just did is I interpolated. Okay? I predicted how many teachers there would be between two values that I knew. I have 10, I have 12, I don't have 11, but I made an estimate. Now, we can also make another kind of prediction. Okay. Instead of predicting between two values that we know, we can predict beyond what we know. Okay, so you can go beyond the end of the table. So we could pick a number bigger and try to make a prediction. So on that second line right below the first one, it says using a graph or its equation 2, and you want to fill in this. Predict a value outside. Or another word for outside is beyond. Okay? It's beyond what we know. That's called extrapolation. All right, so let me go back to my table again. And somebody give me a number of teachers that's beyond the numbers in this list. Okay, not between, outside, beyond, bigger. Kyle? How many? 21. Okay, so what I could do is I could plug in 21 teachers, okay? I could plug that in for x, and I would predict that if there were 21 teachers in the school, there should be 483 students. That prediction that I'm making, that's called extrapolating. I'm predicting beyond the end of my list. Now, what do you think happens as you get further and further and further beyond the data you have? Like, let's say I try to make a prediction for 40 teachers, or 50 or 100 teachers. What do you think I need to be careful about when I'm making this prediction? What about the students, especially as I get further and further away from the data that I know? It grows? But something I really want to be careful about. What do you have to be careful about when you make predictions? Especially as you get farther and farther away from the data that you know. Okay.
The point where your data is too far, or like, I don't know how to explain it.
Would you trust this prediction for 21 teachers?
Probably.
Why? Why is it probably okay to trust it?
Because if you divide it, it would probably give you a class between 20 and 21 students for each teacher.
Okay. Anyone else have anything to add? Yeah?
Like when you get farther and farther away from the data, like your prediction gets less and less accurate.
Yes. Okay, just think of the weather, right? If they try to make a prediction for the weather in 3 hours, is it usually pretty accurate? Can they predict the weather usually 3 hours ahead? Now, what if they tried to predict it 3 days ahead? Is the prediction as accurate? No, because they're trying to extrapolate, but it's further away. And if they try to predict the weather 10 days ahead, that might not be accurate at all, because they're trying to predict something that's way too far away. So if you say, I have 100 teachers, I would say, I don't know if I can use this to predict that, because my data right here, it's way too far away from 100. 20, 21, 22, maybe 8, 9, I could make those kind of predictions. But in general, and I think you might already have this on your sheet, in general, the farther removed a value is from the values that you know, the less you can trust your prediction, the less confidence you can have in it. Does that make sense? It's like trying to predict the weather 10 days out.
Say you had that last number, that 406, so you say 483, that's kind of close.
Yeah, that's not
But
bad.
then it's like, the further you get away, it's like you don't have anything to base it off of.
Right, exactly. All right, so this is a problem in your book. Okay, they gave, we didn't, I don't know if we did it or not, but it was about a geyser, Old Faithful, and this is a formula that predicts when it will erupt.
Say, have you been there, Old Faithful?
Health, yeah. Yeah, it's pretty cool if you ever get to see it.
Did you see it like erupt?
Yes. Yeah. So it predicts how much time until the next eruption based on how long the eruption before it lasted. If the eruption before it is really, really short, it's like the geyser didn't let off a lot of energy, so it'll probably erupt again sooner. But if you had like a really long eruption, it's going to take a while for it to kind of build back up and then erupt again later. All right? So sometimes you have to wait like 40 minutes, sometimes you have to wait maybe an hour and a half. It depends. It can be a little unpredictable. So if you really want to see it, you just got to kind of stand around and wait. So it says here, approximate the duration. That's how long the geyser erupts for. It's usually anywhere from 2 to 4 minutes. So approximate how long it's going to last. If the previous eruption was 77 minutes, and you're going to use this formula to do it. So they told me the previous eruption was 77 minutes.
So it's saying the last eruption was 77 minutes ago, right? Was this written kind of funky?
Yeah.
That's all I'm reading. So guys, what it says there, that doesn't say how long, it didn't erupt for 77 minutes. Like Mr. Hager just said, it takes like 2 to 4 minutes for the whole thing to, all the water to spout out of it. He's saying from the last eruption to the one we're talking about now in this problem, that was 77 minutes ago.
Yeah.
It wasn't 77 minutes long, this is the last one happened 77 minutes ago. It's weird, it's worded a little weird.
So it's like if I said to you the time to the previous bell was 8 minutes. That means the bell rang 8 minutes ago. The time to the previous eruption, that was 77 minutes ago. That's when it happened. So, time, okay? Let's focus on that. Where does time get plugged into that formula? Which letter? Yeah, just time, okay? And what do they tell me to plug in for time? 77. So we're going to plug in 77 for time. And we're going to solve for x. What is x? Shannon?
Eruption duration.
Yeah, it's how long the eruption is going to last. Okay, and again, it's usually between 2 and 4 minutes. Okay, who can tell me my first step to get x by itself here? This is kind of really basic equation solving. Yep. So I'm going to subtract 35. Subtract 35. 7 minus 5 gives me 2. And 7 minus 3 gives me 4. And now my last step. How do we move that 12 onto the other side? Yeah, Nina? Yeah, divide by 12, divide by 12. And now whatever 42 divided by 12 is, that's a prediction for how long the next eruption will last.
It's not exact, Mr. Hager.
Right. So it said, based on this model, the next eruption would last about 3.5 minutes. The longer and longer this time gets, it's like the more and more energy builds up, and then when it does erupt, it'll last longer. So what did it do? 3.5? Yep.
And guys, like, we don't have the chart, that's from the notes on Wednesday. It probably had a chart of X and Y, the amount of time until the eruption, and then how long the eruption took. We probably had that list. That number 77 probably wasn't on the list, right? That's why it was probably in between a couple numbers. That's how it goes along with what we were talking about the slide before this, right? That's why we talked about the interpolation and the extrapolation.
All right, so now the next problem says, how long until the next eruption if the one that just happened was 5 minutes? Right? How long until the next one if this one was 5 minutes? Okay, so the previous eruption, the duration, was 5 minutes. Where would that get plugged in? Josh? That's x. Plug in 5 for x. And what letter are we going to solve for? Y. We're solving for how long. What time will the next one occur? Okay, the time. So y equals, can somebody remind me so I don't have to keep scrolling up, what's the formula? 12 times, in this case, the duration is 5 minutes, plus 35. Okay, so we got 12 times 5, plus 35. So if the previous eruption was 5 minutes, the next one's not going to occur till 95 minutes later.
Like an hour and a half. Hour and 35 minutes to be exact.
All right? So all we're really doing is they tell you one of the two numbers. You plug it in and you solve for the other one.
Now, Mr. Hager, when you went to Old Faithful, did you time it out perfectly that you knew when it was going to go on, or did you have to wait around?
I used this formula.
Did you really?
No, I didn't. There's a phone number you can call when you go there, and it says the next one will be at about 10:47. Sometimes it's off, like
What is that, California?
Old Faithful, Yellowstone. That's
Montana.
Montana, yeah. Montana, yeah. Southern, like the south. Well, if we have a map of Montana, I'll show you sometime. It's in the southern, very, very southern part. All right, so let's take a look at this one.
We want to get on a calculator, let's give them a chance to kind of do this one on their own.
Yeah.
Maybe we say we give them a minute or so just to kind of set both of them up.
Yeah,
Then I don't have to solve them, just set them up.
yeah.
Okay. So guys, take a minute. You don't have to solve them, but for both of them, the first one says approximately how many students would be at a school that has 20 teachers. And the next one said approximately how many teachers would be at a school with 335 students. All we want you to do for both of them is just set up your problem. You don't have to solve it. If you have a calculator and you want to solve it, that's fine. There's some big numbers there, so you may not be able to. All we want you to do is just set them up. Based on the information you're given from both those sentences or both problems, set them up. That's all you got to do.
Okay, just to make sure anybody watching the video that knows geography very well doesn't correct me. Old Faithful, here's Montana. It's just barely not in Montana. It's on the edge of Wyoming. So this is Montana.
I'm wrong.
You're off by about, you could be off by 10 or 15 miles. It's just barely in Wyoming.
Yellowstone was like in Montana. So I
Parts of it are.
just kind of.
Yellowstone is huge. It takes up a lot of space. Yeah. All right, let's take a look, Kyle, you think you can tell me the top equation?
Y equals 21 times 20.
Hold on, I can't hear you, Kyle. 1 second. Go ahead.
Y equals 21 times 20 plus 42.
Yeah. So it says how many students would be at a school that has 20 teachers? He filled 20 in for teachers. Okay? That formula would have come from what you did on the graphing calculator in example 1. Okay, but I gave you guys the formula, so you didn't have to do it. Did you do that out, Kyle? What did you get?
Oh, so no, I did not do that.
All right. Did anybody do out 21 times 20 plus 42? Kaylee?
Y equals 420
Plus 42?
Yeah, plus 42.
So-
And that would equal 460.
Yeah, so. Hey, did anybody get 462 students?
Yes.
So that's the prediction. It might not be accurate, but based on the data we have, that's a prediction. Now, 20 teachers, is that interpolating or is that extrapolating? Go back and look at this list. What is it, Kyle?
The E1.
Yeah, this is extrapolating because you're making a prediction beyond the end of the list. Okay, it's going beyond 18. How about the next one? Equation for that one. Jen?
335 equals 21x plus 1, 2.
Yeah, this time they're giving me the number of students. So that's y. And what did you have equals
21x plus 42.
plus 42? Okay, Bay, what would be my first step to solve this for x?
You would minus 42.
Yep, perfect. I'm going to minus 42. So I need 335 minus 42. So that's 293. And what's my last step? Divide by 21. And let's do that out and see what happens. Okay, so remember, we're dealing with how many teachers should be at the school. So what would it make sense to round that number off to? 14. Okay, you either have 13, you have 14. You can't have 13.7. All right, so for our purposes, we'll just say about 14 teachers. Okay. Now, how about this one? 335 students. Did we interpolate or extrapolate? Why did we interpolate? Yeah, it's inside. It's somewhere between the lowest and the highest. It's not beyond the highest or below the lowest. It's in the middle. So that's interpolating, somewhere in here. Okay. Good. So any questions on interpolating and extrapolating? All right. So the last thing we're going to look at is the difference between the word correlation and causation. Okay, statistically, those mean different things. So if something directly causes a change in another thing, not that it's likely. For example, if you study more, it is likely that you will score higher on the test. But it's not guaranteed. Right? It's only likely. That's not a causal relationship. Studying more doesn't guarantee automatically higher test grades. There is a correlation. Most likely, if you study more, you'll get higher test grades.
So I'm saying causation has to be almost like a guarantee.
Guarantee. Okay, so here's an example of a guarantee, a causation. If you exercise more, you will burn more calories. Okay? Versus, say, take the same
Yeah,
exercise.
you may not lose weight, but while you're exercising, you'll burn calories. It's
Yes.
guaranteed.
Given the same exercise, let's say running. If you run at the same speed for a longer amount of time, or you run at the same speed for a shorter amount of time, I guarantee you if you run for a longer amount of time, you will burn more calories. Okay? That's a causation. Okay? Running longer, burn more calories.
But, Mr. Hager, this wouldn't work. If you exercise, then you will lose weight.
Right,
It's not a guarantee that you'll lose weight.
right. It's not a
You
guarantee.
still don't eat weight. I mean, it's likely, but it's not guaranteed.
Right. So that would be an example of a correlation. If you look at people who exercise and weight loss, there's probably a trend, like a
So, Mr.
positive
Hager, you
correlation.
might want to put that in parentheses, maybe guaranteed next to causation.
This is guaranteed.
It's guaranteed, it's gonna happen.
All right, so the next two sentences, I think you need to copy. Yes,
So guys-
we need to copy these.
Yeah, so from one all the way to causation, then Mr. Hager up above, they're gonna go from one all the way to causation in the first line up there. Yep. So causation is guaranteed.
And if things have a causal relationship, then that automatically means there's a correlation. If things are causal, then they're automatically correlated, but not the other way around. Just because there's a correlation, just because there might be a pattern of exercising and weight loss, it's not a causation. It doesn't guarantee. Okay, so what we're going to do is kind of look at some examples, and I'm going to have you read it and see if you can tell me whether the two things I'm talking about are correlated, meaning that there's likely a relationship,
It's not guaranteed.
but not guaranteed, or is it a causation? If one thing happens, the other thing happens automatically, no question. And I already kind of hinted at one of them. All right, so the example, we're going to be asked to tell whether or not there is a correlation. And if there is, I want to know, is it a causal relationship, meaning one thing causes the other. It's like a guarantee. Because if there's not a correlation, you don't even have to look for causal. Right? Causal is like really strong. Okay, you got to have correlation before you can have a causal relationship. So time spent exercising and the number of calories burned. Do you think that there's a correlation there? I'm not asking if there's a guarantee yet, but I'm saying, do you think there's likely a connection between the time you spend exercising and the calories you burn?
Yes.
At least, most likely a relationship. Yeah. So tell whether a correlation is likely. So yes, there's probably a pattern with exercising and calories burned. Yes, correlation is likely. Now I want to take it one step further and try to say something even
Guarantee.
stronger. Is it a guarantee? Does one thing automatically cause the other? If you increase your time exercising, will that guarantee you burn more calories? Assuming you do the same exercises. Yes. So yeah, this time there is a causal relationship. So I'm going to put there is a causal relationship. But then it asks me to explain. So I'll say, yes, there is a causal relationship because exercising longer guarantees more calories burned. Is it guaranteed?
Causal's a guarantee.
Exercising, what did I say? Because exercising
Guarantees.
longer guarantees more calories burned. That's as simple as I know how to say it. Okay, so there's a causal relationship because exercising longer guarantees more calories are burned. Again, assuming you're putting in the same effort, you're doing the same exercises, you're doing more of the same thing. Same intensity, stuff like that. Okay, the next one. It says the number of banks, just add an S, the number of banks in the population of a city. Do you think that there is a connection between the size of a city and how many banks it has? If you looked at like sizes of cities across the United States.
How many people are here from Fitchburg? Okay, a lot of people, a lot of Fitchburg people, okay. Anybody from, I think about like my wife is from Sterling. Anybody from Sterling in here? How about like Ashburn in here? Who's from Fitchburg? Who's from Fitchburg? Raise your hand.
I'm from a small town.
Shannon, where are you from?
Ashby.
Ashby. All right. So think about it like this, okay? You guys that are from Fitchburg, there's a lot of banks, right? Pretty big city, right? Now think about if you've ever driven through Ashby. Yeah.
There's trees and more.
Yeah, I guess you can compare. Like you can talk about
And a restaurant.
I guess you guys can talk about like Fitchburg and Westminster, right? Guys, listen. A lot of you probably Westminster, right? Like the center of Westminster, right up here, right? I mean, yeah, there's an IC credit union, but right? What about Fitchburg? You got IC credit union, you got Rollstone, you got DCU on John Fitch Highway. There's tons of them, right? So when we talk about this, think about that, right? Fitchburg has a higher population than Westminster, okay? So do you think there's some correlation there? Yeah, it's probably going to be a correlation,
Yeah.
all right?
Yeah, so there is a correlation, I would say. I bet there would be a trend if you made a scatter plot. Bigger cities probably have more banks. So let's put yes. Again, a correlation is likely.
So guys, when you have a correlation, that first sentence that Mr. Hager writes, use that every time. That's the sentence you're going to use.
But is it a causal relationship? Does having more people in a
What does that
city...
mean, guys? Sometime I raise your hand. What does causal mean? Maggie, what's causal mean? Yeah, it's guaranteed. Good.
Is it guaranteed, like automatically, if more people move into a city, a bank automatically pops up?
No.
No. Yeah, you have to build it. It doesn't, so no, there's not a causal relationship. So no,
Guaranteed.
not a causal relationship. And some of this can be vague. A lot of times with statistics, the questions can be vague, but I'm trying to make them as
Yeah.
clear as possible. Okay, things like that. Okay, so does anybody have any question why this one's a correlation but not a guarantee? Just shoving a bunch of people into a city isn't automatically going to make banks pop up. That doesn't work that way.
It'd be nice.
All right, so last one. Okay, again, I want you to tell me whether there's a correlation, because if there's no correlation, you don't even have to worry about the next step. First, tell me if you think there's a correlation, and then whether or not it's causal. So the amount of time spent talking on a cell phone versus battery life left in the phone. Do you think
You did this on purpose to make it longer.
Do you think that there is a connection, some kind of relationship between how much you talk on the phone and how much battery life is left?
Yeah.
Yeah, what do you think happens?
The longer you're on the phone,
Who's about to die?
the power.
Yes, it's probably a negative correlation, right? The more you talk, the lower
What you feel about
the battery. So, yes. And I'm going to put in parentheses this time. I didn't do it last time. but this time it's a negative correlation. The banks and the people, that would be a positive correlation. Okay, now the next part, last part, it says, is this causal? Is it guaranteed if you talk on the phone, the battery is going to go down?
Yes.
Unless you're being weird and probably.
Pretty much.
Yeah, and that's our
Yeah, unless you consider something special, like it's plugged in while you're using it.
Charger.
But let's assume, okay guys, let's assume that it's not plugged in.
Nothing special going on here.
Yeah, then I would say this is a, what do we call this if it's guaranteed? Causal.
It's a opposite.
Yes. This is a causal relationship because talking longer, so I'll put because talking longer guarantees the battery will die quicker. Okay, assuming it's not plugged in, nothing like that. Talking longer guarantees. So you want to put that word guarantees in
Is it
there.
guarantees a decrease in battery life?
Sure. Guarantees a decrease in battery life. Okay, so that's the difference between a correlation and causation. One is really strong, it's guaranteed. The other one, there could be a pattern there but not guaranteed, it's causal.
So guys, that's just about it. Now, what were we talked about 4 vocab words today, all right? Somebody give me one vocab word we talked about.
Correlation.
Katie. Huh? Causal, what's that mean? Give me one word to sum it up. Guaranteed. Very good. What's another vocab word we talked about? Huh? Extrapolation. What's it mean? We're all looking at your notes.
Outside.
Yeah, it's outside the given data. Shannon, what's another one we talked about? Interpolation. What's that mean?
inside.
It's within. It's not a number on the chart, but it's within those numbers. And correlation, right? It shows correlation, but again, it's not guaranteed. All right?
And on the board, guys, I put your homework. Remember, it's not due till the 27th, but we're going to give you guys a little bit of time. You got 10 minutes. You might finish it.
Guys, in order to put your, we have like 9 minutes left. In order to put your stuff away, all right, you at least have to do the first one.